Hello, hello all. Welcome back to our channel Complete Chemistry. Today we'll see about SN2 mechanism, that is substitution, nucleophilic bimolecular reaction with an expression as rate here it will be equal to both concentration of nucleophile and also concentration of your reactant. So this is a bimolecular reaction. It's called so because this rate of reaction is involving both your nucleophile and also your reactant, right? Now, if rate determining steps involves an interaction between two species, that is a nucleophile and organic substrate, we call this as SN2, right? We'll just see the mechanism here. Now, what is happening here? This is your nucleophile. This is your leaving group that is present, and this is the incoming nucleophile, right? Now, what is happening here is this three groups are present here, and your incoming nucleophile will be attacking from the back side to your chiral carbon. Thereby what happens here, your leaving group will be leaving out. So this is your transition state that is formed. Transition state is an imaginary state. It's an imaginary state. There will not be any physical state for this, like physical point like a melting point, boiling point or anything will not be there for this transition state. This is an imaginary state. So this transition state here in your SN2 reactions is a trigonal bipyramidal in shape, where this forms a trigonal structure and then your bipyramidal structure. So as your nucleophile is attacking from this side, your leaving group will be leaving out. So this is a transition state, right? And this is your leaving group with lone pair of electrons, with your shared pair of electrons that are leaving out, and this is your final result, right? This is your electrophilic carbon that has inverted configuration, because the configuration here will, if it is S, then the configuration here will be of R. If it is R configuration here, then you will have your S configuration here, right? Proceeds with, now this SN2 proceeds with single transition state in which central carbon atom is partially bonded to 5 groups. So here this single carbon atom is binding to 5 different groups. So we call this as transition state, right? The next one here is what are the factors involving in this transition state. Now these factors here are, first one is about what type of carbon that is involved, which is getting involved here. In your SN1 reactions, your tertiary butyl carbon is most involved in your SN1 reactions, but here you have your methyl group, then your primary carbon, then your secondary carbon, then your tertiary carbon. So this is your primary, this is your secondary, and this will be your tertiary carbon. I think you must be knowing your primary carbon, right, which is attached to only one single carbon, and all these will be your hydrogens, right? And then this is your positive charge. This is your primary carbon, and then secondary carbon is the one which is attached to two carbons. This is your secondary carbon, and tertiary carbon is attached to 3 carbons, and this will be your tertiary carbon, right? So here methyl groups are more effectively undergoing SN2 reactions than your primary, then your secondary, and then your tertiary carbons. If steric crowding increases around the electrophilic center, the rate of reaction decreases. Why? If it is a methyl group here, if it is only a methyl group here, then only. If this is a methyl group here, what happens? All these three will be your hydrogens, right? Because all these three are very smaller atoms, your nucleophile can easily attack from the rear end side. If these three are your methyl groups along with your carbon will be present like this, right? All your hydrogens will be present like this, and here also if you have methyl group here, you have your hydrogens like this. So these bulky groups will avoid your nucleophile to attack your electrophilic center. So methyl groups here will be effectively undergoing SN2 reactions than your primary, than your secondary, than your tertiary carbons. Then the second point here is the breaking of Cl is a rate determining step. What happens when your breaking of Cl is taking place? Cl is nothing but your C is your electrophilic center along with your leaving group. So this breaking here is involving along with your reagent, that is your Cl, and also your incoming nucleophile. Incoming nucleophile concentration is also involving here. So this is the rate determining step here, because it's the slowest step where your leaving group is leaving out and nucleophile is attacking. So this involves two species, that is your reactant and also your nucleophile that is attacking, right? So here breaking of Cl is a rate determining step. If the leaving group is active, then the rate of SN2 reaction increases, right? Leaving group should be more active. Then the third one here is the nature of nucleophile is very important in an SN2 mechanism, because nucleophile is involved in the rate determining step, whereas in your SN1 reactions nucleophile will not have any action. Nucleophile will not have any action in case of your SN1 reaction, but in case of SN2 this nucleophile is involved in rate determining step. So this is very important point. Now coming to your solvents here, it is polar aprotic solvents that are involved. I said you in SN1 reactions, polar itself means which has bipolar group like your water molecule. Now this will have partial negative charge because of the its attraction towards shared pair of electrons towards itself, and these hydrogens will have partial positive charge because of losing of electrons. Now there is formation of two poles here by pole, negative pole and positive pole here, so we call this type of reagents as your polar solvents. Aprotic solvents are those which will not release out H plus ions. H plus ions are not released out in case of your aprotic solvents. Can you give some examples? Examples are your acetone. So this is your acetone, right? Now here in this group, your H plus ion will not be released out. No releasing of your H plus ions will be taking place in your acetone. In case of your ketones or acetones, in case of your esters, in case of your ethers, your methyl like H plus ions will not be released out. So these are called as your aprotic solvents. So aprotic solvents are your solvents involved in your SN2 mechanism. Now the next point is your important stereochemistry. This is your stereochemistry. Now what is happening here? Now I said alkyl halides are the important reactant species which are going to involve in your nucleophilic substitution reactions, right? So the nucleophile attacks in an SN2 mechanism on the opposite side, to the position of the leaving group. As a result, the reaction will proceed with the inversion of configuration. See here, this is your incoming nucleophile and this is your leaving group. Now this is attacking from the rear end side, opposite side, and this will be leaving out. So this is your bond, this is your transition state that is formed, trigonal bipyramidal transition state. Now what is the configuration here? Now this is given as number 1, this is given as number 2 because 2 carbons are involved, and this is your 3 and this is your 4, right? What is the rotation here? Now 1, 2 and then comes to this, but your hydrogen, that is 4 numbered carbon, is not present on the dotted line, right? Dashed structure. So we need to reverse this configuration. So this is clockwise rotation, this is R configuration. As hydrogen is not present on the dashed structure, we need to reverse this configuration and say it as S2 bromobutane, right? S2 bromobutane. Now after formation of your final product, what happens here? Your alcoholic group like OH group is adding onto the back end side of your electrophilic carbon, and your leaving group will be leaving out with your shared pair of electrons, right? Now what is happening here? Now remember, this oxygen will be given number 1, this will be given number 2, methyl group is given number 3, and your hydrogen number 4, right? Now when you rotate this, what will happen? Now this is your anti-clockwise rotation, this is S, but hydrogen here 4 numbered species is not present on the dashed structure, so we need to reverse this configuration and then say it as R. So the configuration here is R2 butanol. So we call this as inverted configuration and inversion configuration. This was first discovered by a scientist called Walden. So we say this configuration as Walden inversion configuration. Sometimes in questions you may be asked like write about Walden inversion configuration mechanism. Then you need to write about your SN2 reactions only, right? So this is your Walden inversion that is involved in your stereochemistry of your SN2 mechanism, right? Now we'll see your energy profile diagrams here. You'll just compare your SN1 and SN2 energy profile diagram. What is it? Like if you take your on your y-axis energy here and your SN1 reactant mechanism, like if your while the reaction is proceeding, first your reactant is Rx and your nucleophile. Your nucleophile is not acting, not having any type of action in case of your SN1 reaction. So nucleophile will be as usual, right? Now there will be formation of your rate limiting transition state. This transition state is just imaginary state, but what is important that is formed here is your carbocation. Carbocation is formed here as an intermediate. Carbocation intermediate is formed. Now this carbocation intermediate will have melting point, will have boiling point and all types of physical state. But transition state will not have any melting point or boiling point. This is an imaginary state. That is a very important difference between your intermediate and transition state. Now after your intermediate is formed, your nucleophile attack takes place to your carbocation. Thereby there is a formation of final product. The energy will be still more decreasing, right? Now this is your energy profile diagram of your SN1 reaction. But coming to your SN2 reaction, when you take your energy on your y-axis and SN2 mechanism on your x-axis, as it proceeds, what happens here is this nucleophile is involved in the reaction of bond breaking between your R and X, and there is formation of transition state. Single transition state is formed here. Single transition state is formed, and the final product with your nucleophile leaving group will be left out, and incoming nucleophile will be reacting with your carbon, that is electrophilic carbon, and forms your final product. This is your energy profile diagrams of your SN1 and SN2. These two are also very important in all the main exams. So this is about your SN1 and SN2 mechanisms that are present. Please watch my videos. Please like, share and subscribe to my complete chemistry.